The only graphs that I want you to be able to graph on your own are the sine and the cosine graphs. However, I do want you to be able to recognize the other graphs. So we're going to look at those today. You will have a quiz next week, whatever our day 2 next week is. Next week's a short week, right? So this is 6th period, so we'll have a quiz Wednesday, and it will be matching, okay? And basically, you're going to have to be able to match the graphs. So let's start by looking at tangent. So you all need to be taking notes, and you need to have your calculators out, okay? So to start with, let's talk about the period of tangent. Because what's the period of sine and what's the period of cosine? 2 pi, right, 2 pi. So your basic sine function, sine curve has a period of 2 pi. What does that mean?
It completes a cycle every 2 pi.
Right, it completes one full cycle in 2 pi units. That's what that means, okay? So let's look at tangent, all right? Let's just kind of look at the unit circle for a second, all right? And let's look at some of the values for tangent. Okay, so here at 30 degrees, we have tangent, remember, is y over x, right? So at 30 degrees, we're going to get 1/2 over the square root of 3 over 2. That's the y over x. Everybody good with that? Okay, how about at 45 degrees? What's the tangent going to be? Over square root of 2 over 2, right? And I'm not worried about simplifying it right now. Actually, let me, I'm going to redo that a little bit bigger so it's not so cramped. Okay, let's try again. Okay. So, well, that's not bigger, is it? What in the world is wrong with me? Let's try that again. I said make it bigger, and I really didn't make it much bigger. Okay. All right, so right here at 30 degrees, we're looking at y over x, so that's 1/2 over square root of 3 over 2. At 45 degrees, we've got square root of 2 over 2 over square root of 2 over 2. At 60 degrees, we're going to have y over x, so square root of 3 over 2 over 1/2. Okay, so if we wanted to figure out the tangent at those values, that's what we'd be looking at. Over here, the x is negative and the y is positive, so we'd get negative root 3 over 2. Did I do that right? Yes. I'm sorry, positive root 3 over 2 over negative 1/2. Right, so the whole thing's going to be negative. Here we're going to get root 2 over 2 over negative root 2 over 2. And here we're going to get 1/2 over negative root 3 over 2. So basically the same values, but negative. Well, look what happens when we move down to the third quadrant. They're both negative, but when I do a negative over a negative, I get a positive. So I'm actually going to get, I'm going to get the same values that I had in the first quadrant, right? I get all the same values. Do you see that? What's going to happen in the fourth quadrant? Is it going to be positive or negative? It's going to be negative because the y is negative and the x is positive. So I get a negative, which means I'm going to get the same values that I had in quadrant 2. Based on that, what is the period of my tangent function? Pi, yeah. The period is pi because after we go pi or 180 degrees, it actually starts to repeat itself. Okay? So the period is pi. Okay, let's look at some other things about tangent. Because tangent is a quotient, I've got an x in the denominator. There are going to be some places where it's undefined. So where is tangent undefined? Right? Remember, tangent is y over x. So what would make that fraction undefined? Yes, Gavin. When x equals 0, right. Well, let's see, where is that? So this point here, this is 1, 0, so that's when y equals 0. Here we have 0, 1. That one, I'm going to get an undefined tangent. So I'm getting an undefined at pi over 2. Let's see, over here we have negative 1, 0, so that's okay. And then down here I have 0, negative 1. That's going to give me another undefined. So 3 pi over 2. Okay? So we've got an undefined at pi over 2 and at 3 pi over 2. Okay. Let's go up to our graph. Okay, I'm going to graph 0 to 2 pi. Okay. There's pi, and here's pi over 2, and here is 3 pi over 2. Okay. What's going to happen, it's going to be undefined at pi over 2. I'm actually going to get what we call a vertical asymptote at pi over 2. So in other words, the function's going to go as close as it can to that pi over 2, but it's never actually going to be pi over 2. And then the same thing's going to happen at 3 pi over 2. So I get these vertical asymptotes. Okay. Now, if I go the other direction, so I go all the way over to negative 2 pi, negative pi, negative pi over 2, negative 3 pi over 2. Okay. So if we go in the negative direction, I've got the same thing that's going to happen. It's going to be undefined. Instead of 3 pi over 2, what would we call it? Negative pi over 2. So it's going to be undefined at negative pi over 2. And it's also going to be undefined where? Negative pi over 2 and negative 3 pi over 2. Right. Oops. 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 Okay. Okay, so there's all my undefined points. Okay. Where is tangent equal to 0? Where is tangent equal to 0? If tangent is y over x, where is that going to equal 0? Right, it's going to equal 0 when the y is 0. So it's going to equal to 0, right, when y equals 0, which is at 0, at pi, at 2 pi. Okay, so let's go back up to our graph. It's going to equal 0 at 0, at pi, and at 2 pi. How about going in the negative direction? Negative pi and negative 2 pi. Okay? So I've identified my period is pi. I identified where it's undefined and I identified where it's 0. Okay? The rest of it, I'm just going to tell you what the shape is because, like I said, I just want you to recognize it. And they almost look like little cubic functions, right? Kind of. So it actually looks like this. And it's going to keep doing that same thing over and over and over again. Every pi unit. Now, on this end, right? So it goes from pi over 2 to pi, right? So every pi over 2, we kind of get half the curve. So it's going to be like that. And then on this end, so this is kind of like, right, if I were to extend this out further, it would be going like this, right? So here we're getting the top half of it. Okay. That's your tangent function. Very different than sine and cosine. Tangent's pretty easy to recognize. Okay. So that's your tangent function. Okay. I would want you to be able to recognize translations of that function. Okay. So for instance, if it was tangent x plus 1, what do you think would happen? Yeah, the entire curve, the whole thing would shift up 1. So in other words, where it's crossing the axis, that's going to shift up 1 to like going like that. The whole thing is going to shift up 1 unit. So I'd want you to be able to recognize that also. Okay. It's going to look kind of like that. Okay. What do you think would happen? Let me just put these back now. Okay. What do you think would happen if we had y equals 3 tangent x? Because that 3 represents what? The amplitude. It represents the amplitude, right? So on a sine curve, right? So instead of just going like this, right? If it was 3, it's going to go up higher and down lower, right? So on a sine curve, it's very obvious. What we're actually doing when we do that is a vertical stretch. Right? When that sine amplitude reaches up further, we're taking that normal sine curve and we're just kind of stretching it up, right? So what's going to happen here? It's going to stretch up, and it may not be that obvious to us, right? So if I give you a quiz with matching, like how are you going to know? So let's look at this on our calculator. Okay, first I'm going to put in tangent x. Okay, so go ahead and get your calculators out. Anybody need a calculator? Oi! Oi! This is an honors class, you people!
Semi-cars.
Man! Oh, she. Oh, excuse me. Okay. What mode do we have to be in? What mode? Radians. Yes, we need to be in radian mode. Okay. All right, now we're going to adjust our window. Now, you may not have that first option that says shade res on there, okay? So our x min and our x max. So this is just a tangent function. So we're going to graph this from, we're going to go from negative 2 pi to positive 2 pi. Oops. Negative 2 pi to positive 2 pi. When you press enter, it changes it to decimal. All right, we're going to go by increments of pi over 2. And we can leave it, the y value, negative 10 to 10. That's fine. Okay, let's graph it. Okay, there's our tangent function. Okay. All right, let's look at what happens if we make it tangent, a 3 tangent x. So in y2, I'm going to leave tangent there. In y2, I'm just going to put 3 tangent x. The window is going to be the same, so I don't have to regraph it. Readjust it. So I press enter. And there you go. So what it's done, it's a vertical stretch. So it's taking that blue curve, that blue one that's tangent x, and it's just stretching it, right? It's taking this blue one, just imagine grabbing it up here at the top, grabbing it at the bottom, and then just pulling it apart. Okay, so that's what it's doing. It's stretching it. So when we do that, the curve becomes less obvious, less severe. Okay, so if we look at just the tangent or 3 tangent x, okay, it still has that shape, but it's not quite as severe, right? If I change that to maybe a 7, right, it's going to be less severe. Right, the curve is getting less and less obvious, okay? Okay. That's your tangent function. Can you, yes?
Well, is it like end up looking like a normal line and it's stretched?
If it's stretched significantly, it could, and we call that local linearization. So basically, so let me see. I'm not sure if I can accomplish it on this calculator or not. Let's try. Okay, I'm going to do like 90. How about that? That's really significant, right? So that's a pretty significant stretch. It almost looks like just straight lines, right? So I think, and I haven't tried this, but in theory, if I zoom out enough, I should start to see some of the curve. Now, the problem I'm going to run into, I think, is that when I'm zooming out, I think those red lines are going to get so close that we're not going to be able to really see it. But let's just, yeah, that's what's happening. Oh, not quite. Yeah, now it's getting really crazy. Okay. So, but that's what's happening, right? If we were able to zoom out far enough to see, we'd see that curve, but there's some limits to what our calculator can do graphically, okay? Yeah, we call that local linearization. So what that means, if I were to zoom in on a particular little section of it, it'll look linear, although it's not actually linear, right? That's why you have to understand your functions a little bit instead of just plugging them into your calculator, okay? Okay, what do you think, right? Actually, I think what I'm going to have you just talk to your person next to you. What do you think y equals cotangent x will look like? I'm going to give you like a minute to discuss it. Think about what we just talked about. Think about your asymptotes. Think about your zeros, all that stuff, okay? So I'm going to give you like a minute to talk to your neighbor. I like the conversation I'm hearing. I'm hearing you guys really think about it, right? So let's, I'm going to just do it in a different color, right? Let's talk about it. Well, first off, will the asymptotes be the same? Right? Tangent is y over x. What's cotangent? X over y. So will the asymptotes be the same? No, because now I'm looking to see where the x is equal to 0. Right? So this is going to be x over y. So we're looking to see where the, where the y is equal to 0. Sorry about that. So we're looking at 0, pi, 2 pi, right? So our asymptotes are going to be different. So let's move those. I think pretty much everyone I heard saying that it's going to be a similar shape, right? So we're just moving it. What about the period? Do you think the period's going to change? Is the period going to be pi or 2 pi? How did we determine the period? When it started to repeat itself. So cotangent, how long is it going to take for cotangent to repeat itself? We're going to use the same reasoning, right? It's going to be pi. So the period is the same, okay? Let's find out where the zeros are. We're looking at x over y. So we're looking to find where that is equal to 0. And that's going to be where the x is 0. Right? That's going to equal 0 when x equals 0, which will be at pi over 2, 3 pi over 2. That's going to be the zeros. So already we are seeing a difference, a kind of a significant difference, right? We have different asymptotes. We have different zeros. Okay, so here's my zeros. Okay, let me get rid of these others. Oops, come on. There we go. All right. I'm really tempting fate here, huh? Okay, it doesn't want to do that. Okay, so the other thing that's different is the direction that it goes. So instead of going this direction, it's going to go the other direction. It's going to go like this instead. Okay? So I know it does mathematically this is nothing, but in my brain, I don't know. I always think of co's as being like negatives or opposites. That's just how my brain translates it. So tangent, right? Tangent was going this way, and that kind of feels like the right way because we're going up as we're moving from left to right, you know. So the cotangent going down as I'm moving from left to right just sort of makes sense in my weird math brain. Okay, it's just co's are kind of like wrong, you know. So it just makes sense to be going downhill as I go left to right. Right. So I know in general, I know it's going to be going downhill like that. The part that I have to really focus on is, okay, where's the axis, where's the vertical asymptote, and where's it going through the x-axis, right? So that's going to be our cotangent function. Okay? And again, you should be able to recognize it if it's being stretched or if it's being shifted up or shifted left or right. Okay? Again, I'm going to give you a quiz. It's all going to be multiple choice. Okay? I mean matching, not multiple choice, all matching. Okay, let's move on to secant and cosecant because these are weird. These are really, really, really weird, right? So let me get rid of a whole bunch of stuff here. And what I'm going to do is I'm going to kind of sketch in the sine curve. Actually, you know what? Let me do it on the calculator. That'll be quicker. Okay. So I'm gonna graph sine x, and I'm just gonna change my window a little bit. I'm gonna make it like -5. Oops, shoot. -2 pi to +2 pi. And we're gonna go by increments of pi over 2. And I'm gonna go from -5 to +5 on the y-axis. Okay, there's my sine curve. Okay. Now let's talk about cosecant. If you remember, cosecant is the reciprocal of sine. So that equals 1 over sine x. Okay? Which means I do have some places where it's undefined. Where do you think it's going to be undefined? Okay, where do we think it's going to be undefined? Where the sine is equal to what? 0. And sine represents, is it represented in y? Okay, so it's where the y is equal to 0. So it's going to be undefined at 0, pi, 2 pi. That's where it's undefined. So we're going to put our undefined line in there. 0, pi, and 2 pi. And of course, I'm going to go the other direction also.
Attention teachers and students, pardon the interruption at this time. Can we please dismiss our track and field team? Thank you.
Okay. Make sure that you check the video, okay? All right, so we've got cosecant is undefined, right? So what do you think the period of cosecant is? Pi over 2? Why is that? So the period, what's the period of sine? Oh, I see why you think it's pi over 2. Okay. What's the period of sine? 2 pi. Because it takes 2 pi, it takes 1 full time around the circle before it repeats itself. So if cosecant is just 1 over sine, it's still going to take 1 full time around the circle to repeat itself. So let's look at what cosecant is on the graphing calculator. So cosecant is 1 over sine. There's no cosecant on your graphing calculator, so we're going to put it in as 1 divided by sine x. Okay? Okay. There's my cosecant. Isn't that weird? So look at it, right? So you've got an upward loop, a downward loop. That's one cycle. Then you have an upward loop and a downward loop. That's another cycle. So it is taking 2 pi units to complete its cycle. Okay? So when I'm graphing this, right, if I go back up here, okay, I'm just going to sketch my sine curve in there real quick. Right? Here's my sine curve. Okay. When you're graphing this, you're going to make a U, and the U is going to touch the amplitude of the sine curve. Okay, so the U is touching the amplitude of the sine curve, like that. Okay, so if I were to continue this sine curve over here, okay, there's my sine curve. Again, my cosecant is a U. We're going to keep the U within the boundaries of those vertical asymptotes, but it's going to touch the sine curve like that. Okay? And of course, this is actually not part of the graph, right? The actual cosecant function does not include this curve. Okay, get it out. There you go. Okay. Oops. So that's what your cosecant curve would look like. Yeah.
All like individual things, or are they like all connected?
They're not connected. Good question. They're individuals because remember, these are asymptotes. It's undefined on here. So in order for this end to be connected to this end, it would have to at some point touch this line. And it's not going to because it's never going to equal that value. Very good question. And that's a really important thing to understand because some of your older calculators will connect those. Okay, some of your calculators, when it graphs it, if you're using an older one, it'll do this. Okay, and it gets very confusing looking because you have these extra lines in there going like this. The reason it does that, the calculator's algorithm, okay, those of you that are taking computer class, the way the calculator is plotting your graph, it's literally plotting points and connecting the points. Well, the calculator has a finite screen, so there has to be some point where it says, okay, that's as far as I can go on your screen. So it looks at this point and it connects it with the next point that it has, which is this point down here. That's why some of your older calculators put that extra line in there that's not actually part of the graph. That's, again, you have to have a basic understanding of your graph when you're using the graphing calculator. That's why many Algebra 1 classes don't allow the students to use a graphing calculator because we want you to get an understanding of your graphing first, okay? What do you think would happen? How would this curve change if it was y equals 3 cotangent x? How's that going to? It could be. I'm not sure I'm not sure that's going to be obvious though, because of what we see when we graph. So it might be skinnier, but remember these ends, right? These ends are going to continue to go out. So it's still going to go out to come close to these two lines here. So yes, it will be skinnier, but there's another significant change that makes it even easier to see. Let me ask you, how did we know where to start the U? Right. The U, right? So on the cotangent function, that U, the bottom of the U is at 1 because it has an amplitude of 1. So if we had an amplitude of 3, the bottom of the U would be starting at 3, right? So let me put that on the graph here. Let's see, I'm going to take So 3 times cosecant is 3 times 1 over sine. So I can enter that as 3 over sine. 3 times 1 over sine is 3 over sine. Does everybody understand that? Okay. So let's go ahead and I'm going to remove this one. Let's graph that. There you go. See how it starts way up now. Okay. So those u's are skinnier. Let's put our regular cosecant back in there. 1 divided by sine. Oops. Yes, Annalie.
How come sine to the negative 1 doesn't equal 1 divided by sine?
Anybody remember why that is? Well, why don't we just use sine to the negative 1? Sine to the negative 1 is the inverse sine, and that's what we use to find angles. So sine to the negative 1 is actually not 1 over sine. Okay. Okay, so Grant, look, you were right. It is skinnier, but it's hard to recognize that it's skinnier unless you're comparing it to the original function. Now we can say, oh, it's definitely skinnier. So it's more recognizable to look and see where it's starting based on the amplitude. Okay, a good observation. Okay, we've done sine, we've done cosine, tangent, cotangent, cosecant. What have we not done? Secant. We didn't do secant yet. Okay, so let's look at secant. Secant and cosecant, how are we going to tell the difference between them? Well, let's discuss secant rather, and see what we know about it. Okay. What do we know about secant? Well, we know that equals.
Y is above 0, is it going to be not a regular U, but
You think it's going to be like an upside down U?
Yeah.
Good thought. Okay, good thought. If it's secant is 1 over cosine, right? Cosine has a period of 2 pi, so we're looking at the same period. Where's it going to be undefined? 1 over cosine. Where x is 0. Where x is 0. That will be pi over 2 and 3 pi over 2. All right, so right away we know we're moving our asymptotes. Got to move them again. So it's going to be undefined at x equals 0 and at pi over 2 and at 3 pi over 2. Okay, and then it's going to be undefined here at negative pi over 2 and at negative 3 pi over 2. Okay, let me clean up my mess here a little bit. Okay. Okay, so there's my asymptotes. Now let's talk about where secant x will equal 0. Will it equal 0 anywhere? No, because I can't, in order to equal 0, I'd have to have a 0 on the top, and that's not going to happen. So it's never going to cross the axis, right? All right, so let's see what it looks like. Let's graph our secant x. So again, this time I'm going to graph cosine. I'm going to graph cosine there. And this is going to be 1 divided by cosine, because that's what secant is, right? And check my window. Okay. So, oops. So here's my cosine function, okay? It looks like sine, right? But if you only look at this part of it, the right side, now you recognize that as your cosine function, right? But then remember we said cosine is basically sine just moved over, okay? So now let's graph our secant. Same thing happens. But what's the difference? It's shifted over. Okay? let me just show you. Okay, I'm going to put sine. Okay, here's my sine x, and here's my 1 over sine. Okay, so I'm going to, you kind of have to watch, all right? So here's sine and cosecant. This is the one we graphed before. There's sine and cosecant. Okay? Now I'm going to graph the cosine in there. I'm going to put cosine there. Let me remove the cosecant here. Okay. The blue one is sine. I'm sorry, the green one is sine. The blue one is cosine. Okay. Notice they're the same curve. They're just shifted over pi over 2, right? If I go to my sine function and I tell it to shift to the left pi over 2, so in other words, I say add pi over 2. I'm sorry, did that the wrong way. Inside here, I do add pi over 2, right? That's going to shift my sine curve pi over 2 to the left. Watch what happens. The blue one is cosine, the green one is sine. There's the blue. Look at that. Now they're the same. Let me show you that again, all right? Save myself some work here. Sine x. Here's my cosine and my sine. The green one is sine. Everybody needs to look up here. You need to see this, all right? The green one is the sine curve. They're the same curve, except shifted over, right? If I tell it to shift sine pi over 2 to the left, that's what adding pi over 2 there does. Okay? It ends up being the exact same thing as cosine. So now let's look at it in terms of secant and cosecant. Okay, so here's my secant. Okay, here's secant. Cosecant, what's that going to do? It's going to shift it to the left, or I should say either direction, pi over 2. There you go. It shifted it pi over 2. So it's the same thing. It's just shifted over. So when we look at the curve here, right, if I draw my cosecant curve, okay, here's cosecant. Let's see. All right. So here's my cosecant curve right like this. Okay, and we're going to continue. It's weird. I can't draw that certain direction. Okay. It's going to continue like that. There's my cosecant curve. So my secant is going to do the same thing. We've got u's that are touching the amplitude. U's that are touching the amplitude. Okay, now this u over here, this is only going to be part of the u, half the u. And this will be half of the u right there. So secant looks just like the cosecant, just shifted over. Okay? Questions? Okay. So, let's review. Okay, let's graph. I want you guys to take out, or you can use your notes or whatever, but I want to take out a blank piece of paper so you have room. We're going to graph all 6 trig functions, okay? So first we're going to graph sine. Y equals sine x. I want you to graph y equals sine x. And then I want you on a separate graph, you're going to graph, so you're going to do 6 separate graphs. Y equals cosine x. And then you're going to do y equals tangent x. 6 separate graphs. Y equals cotangent x. Y equals secant x. And y equals cosecant x. Okay? You're gonna spend the rest of the period doing this. Try to do it without looking at your notes. Okay? 6 separate graphs, and you're going to graph from negative 2 pi to positive 2 pi. Okay? Everybody got that? Try to do it without the graph if you can, without your notes. Pay attention to the asymptotes. Pay attention to where it's undefined. Pay attention to where it equals 0, which means it crosses the x-axis. Okay?